Hi everyone, myself Dr. K. Srinivasrao, working as a professor in the Department of CSE AML at G. Pullareddy Engineering College, Karnool. So in the last video, we had discussed about the concepts related to process, like what is a process, what is a PCB, what are the operations and how to create a process, etc. And in this video, we'll discuss about the process scheduling. So we'll see what is the process scheduling. So whenever a program or a process is created, actually it will be stored under the main memory. If at a time, for example, one program is ready to execute, then no problem. The CPU will be allocated to that single process and it can start the execution. So here there is no any problem. For example, the main memory is having multiple number of the processes, multiple number of the program, and at a time two or more number of the programs wants to execute. Two or more processes are ready to execute, but actually this should not be happen. So only one process has to execute at a given time, at a time. So if multiple processes are ready to execute, then the operating system will perform the process scheduling with the help of process scheduler. So after performing the process scheduling, the operating system will select one process for the execution. And for that selected process, the CPU will be given. And after allocating the CPU, the process can start the execution. So for that purpose, we can use the process scheduling. It means if multiple processes are ready to execute, then one process will be selected for the execution, and for that selected process, the CPU will be given. And the main goal of this process scheduling is maximize the CPU use. So the CPU will do some operation at any time. So for the better performance, what we can expect is always the CPU should be busy. We cannot expect that the CPU will be idle. If it is idle, nothing will be done. So no operations will be done. So for the better performance, always we can expect that the CPU will be busy. So automatically the performance will be increased. So the main goal of this scheduling is to maximize the CPU use. So in this process scheduling concept, there are three queues are required. One is the job queue, and second one is the ready queue, and the third one is device queue, or also called wait queue. So we'll see one by one queue. The first one, job queue. So this queue contain all the processes which are present in the system. So whenever the processes are created, then they are placed in the form of a queue called job queue. Let us take the example, three processes are created, P1, P2, P3. So three processes are created and these three are placed in the job queue. Okay, and the second one is ready queue. So this ready queue contain the processes which are ready to execute and waiting for the execution. So those queues are placed in the form of the ready queue, which are ready to execute and waiting for the execution. Let us take the example. Here there are three processes in the job queue, P1, P2, P3. For example, the two processes P1 and P3. So P1 and P3 wants to execute. They are ready to execute and waiting for the execution. So then these two processes are placed in the ready queue. Okay. So P1, P3 are placed in the ready queue. And here in the last video, we had discussed about the PCB, process control block. Each PCB having some information about the process. Here in the case of the ready queue, we have a header, and this ready queue header contains the two pointer. One is to the first PCB and also it points to the last PCB. So here for example, there are two processes here in this example, P1 and P3. So first, this is the first process and second process, each one having one PCB. So the ready queue having pointer which points to the first PCB and last PCB. And each PCB also includes a pointer contained to the next PCB. Here we have the two processes P1 and P3. So there should be some pointer from P1 process to P3. So with the help of the pointer, we can identify that after the P1 process, P3 process is there. So these are the two here points. Every ready queue header contain a pointer to the first PCB and the last PCB, and each PCB contains a pointer to the next PCB. So to identify what is the next process in the ready queue. This is the ready queue, second one. And the third one is a device queue or waiting queue. So device queue or waiting queue is nothing but this queue contains the set of the processes which are waiting for the particular device, like input device or output device. So whatever the processes wants to do the input or output operation, they want to access the device, input or output device. So they should be wait for accessing the input or output device. So those processes are placed in the form of the device queue or wait queue. So in our example, P1 and P3 are ready to execute. For example, P1 wants to access any one of the device, then P1 will be placed in the device queue. So at the time of the P1 execution, P3 will be idle. P3 process will be idle. So P1 can start the execution. While execution of the P1 process, if it requires input or output device, then P1 will be wait for some time. So then that P1 process will be placed present in the form of the device queue. Whenever it is placed in the device queue, then P3 process is available. So P3 process is available and the CP will be allocated to P3 and P3 can start the execution. So like that, the device queue or the wait queue contains a set of the processes which are waiting for the input or output device. So these are the three queues required in the process scheduling: job queue, ready queue and device queue. And one more point here, for every device there is one separate device. For input device, multiple types, we have multiple device queues, and for every output device we have multiple number of device queues. So for every device there is a separate device queue. So this is the representation of a process scheduling. We can call this diagram as a queuing diagram. Initially, all the processes are present under the ready queue because they are ready to execute. So if multiple processes are ready to execute, then with the help of the process scheduling, one process will be selected, and for that selected process, the CPU will be allocated. Once the CPU is allocated, the process can start the execution. Okay. For example, if there is no requirement is required for the process, so automatically the process can continue the execution. If any device access is not required, the process can continue its execution. Simply after some time it can stop the execution. So without any accessing, the process can do the execution. Sometime it will stop the execution. This is the first case we have. And second case, while the process is in the execution with the help of the CPU, it is in the execution. So in the execution, there are some situations we can have. One is first one is IO request. It means while execution of a process, the process wants to access any one of the input or output device. So then it will make the request for the operating system to access the input or output device. So whenever the process wants to access any one of the input or output device, that process will be placed in the device queue or wait queue. So already we have discussed about the device queue or wait queue. If it wants to access the device, then it will be placed in the device queue or wait queue. And after accessing the input device or output device, again the process has to restart the execution. So then the process will be placed again in the ready queue. So again, why it is placed in the ready queue? Because here the process wants to access the device, and it is placed in the ready queue. So during this time, the CPU will be idle. So instead of present in the idle state, the CPU will be allocated to another device. So at that time, so for that reason, the first process will be again placed in the ready queue. And whenever the CPU releases the second process, it means second process execution is completed, the first process can start the execution. So this is the first case we can have. So during the execution, IO request is required and waiting for the queue, and again placed in the ready queue. And second case arised is while execution of a process, if some time slice is expired. Like in the next video, we'll discuss about scheduling algorithms, like example, round robin scheduling algorithm. In that algorithm, every process has to complete its execution within the time quantum. If its time quantum is expired, automatically the CPU will be given to the next process. So like that, while execution, if the time slice is expired, the time period is completed, expired, so the current process execution will be stopped and the CPU will be given to another process. At that time, the first process again will be placed in the ready queue. So this is the second situation we can have. And the third situation is the process is in the execution, parent process, and the parent process wants to create a child process. So it can create the child process with the help of some commands or system calls. So parent process has created the child process. Then the parent process, already in the last video we discussed, whenever the child has created, the parent process will wait for some time until the child process terminated the execution. So, and then after that the child process terminated, again enter into the ready queue. This is the third situation. And fourth situation is the process is in the execution with the help of the CPU, and during the execution, if an interrupt occurs. So interrupt is nothing but breaking signal which stops the execution. So whenever interrupt occurs, the execution will be stopped. Then that process will be placed in the interrupt waiting queue, and after handling the interrupter, again it has to restart the execution. So for restarting the execution, again it has to enter into the ready queue. So like that, we can represent the process scheduling with the help of the queuing diagram. If there is no other accessing, just simply ready queue CPU and stop the execution. Otherwise, any one of these four situations may occur. So called queuing diagram. And here we'll see what are the types of the scheduler. So there are mainly two types of the scheduler. We can call it as a short-term scheduler, and the second one is a long-term scheduler. The short-term scheduler is also called CP scheduler, and long-term scheduler is also called job scheduler. So just now we have discussed about the CPU scheduling. Okay, it is nothing but, first we'll see the job scheduling. So job scheduling is nothing but immediately after creating the process, it should be loaded into the main memory. For example, if there is no available space for the new program into the in the main memory, then by applying the job scheduling, one job will be selected and that job will be replaced with a new job or new process. So we can call it as a job scheduler. And this one, short-term scheduler, are called CP scheduler. So already we had discussed it. It is also called process scheduling or process scheduler. When this will be applicable, when multiple processes are ready to execute, then one process will be selected for the execution, and for that selected process the CP will be allocated. So that is the difference between the short-term scheduler and the long-term scheduler. And the difference between the short term and long term, another difference is This short-term scheduler is executed frequently. It is nothing but for millisecond. For every millisecond, it will be executed. It is nothing but for every millisecond, a new process will be executed, selected for the execution. So it is very fast, milliseconds. Whereas the long-term scheduler is executed infrequently, like for seconds or for some minutes, the long-term scheduler is executed. So that's why we can call it as very slow. The short-term scheduler frequently fast, the long-term scheduler is infrequently slow. And this long-term scheduler also controls the degree of multi-programming. It is nothing but the number of the programs present in the main memory. So to control that number, the long-term scheduler is used. So to control the degree of multi-programming, the long-term scheduler can be used. So these are the two types of the scheduler, short-term and long-term scheduler. So based on the time spending the process, we have the two types of processes. One is the IO bound process and CPU bound process. It is nothing but IO bound is nothing but the process will spend more time in performing the IO operations. When a process is spending its more time in doing the IO operation, then the process is said to be IO bound process. It means mainly it is bounded to perform the IO operation. Its main time was given for accessing the IO devices. And the second one is a CPU bound process. It is nothing but a process which spends more time for doing the calculations. If it is in the calculation more time, then we can call it as a CPU bound process. So two types, CPU bound and IO bound. So see the here. So just now we had discussed the two types scheduler. One is the short term scheduler and the second one is the long term scheduler. There is another type of scheduler called medium term scheduler. So this scheduler is used for decreasing the degree of multi-programming. Why you have to decrease the degree of the multi-programming is, degree of the multi-programming is nothing but the number of the programs placed present in the main memory. If more number of the programs are present in the main memory, then accessing time will be increased, and always frequently you have to do the job scheduling. So that's why for decreasing the access time, for increasing the performance of the main memory, and for reducing the number of job scheduler operations, you have to decrease the number of the programs present in the main memory. So for decreasing the degree of the multi-programming, we can use the medium term scheduler. So how this medium term scheduler will decrease the degree of multi-programming is, whatever the processes not required for the execution. It means a process started the execution and it is waiting for IO. Whenever it is waiting for IO device, it will be waiting. Instead of waiting, it is in the main memory, the space allocated for that process will be wasted. So at that time, the process will be taken out from the main memory and stored into the disk as a backing store. And whenever if it is required for the execution, again it will be taking back from the backing store to the main memory, and then it can restart the execution. So this is called swapping. So remove the process from the main memory and store on the disk, and again bring back from disk to main memory and continue its execution. So like that, the medium term scheduler can decrease the number of the programs present in the main memory. So this is the diagram here. Here we have the ready queue and CPU. If there is no accessing required, just simply it can continue the execution and execution will be stopped, terminated. For example, during the execution, if a process is waiting for IO device, it will be placed in the IO queue or waiting queue, device queue, and after accessing the IO device, again it will be placed in the ready queue. This is the second case we have. And the third one is, while execution of a process, if it is required, accessing of IO device is required, then instead of place the process in the main memory, the process will be swapped out, means deleted from the main memory. The process will be deleted from the main memory so that we can have the empty space. So that empty space will be useful for the another process for storing purpose. And after removing the process from the main memory, so that will be placed in the packing store like on the disk. And after that, whenever the process is ready to execute, again the same process will be swapped in. Swapped in means from backing store to memory. Again, then it can ready to execute. So like that, the medium term scheduler can be useful. So thank you for watching the video.